Okay, so today we're going to talk about radio navigation. This is an old omni-bearing selector. Push in, you select which direction you want to go. Things have changed a lot since just look at the size of this thing. It's the size of my head. Um, Now you can get better navigation on much smaller devices. A lot of times it's just like a small brick, if that, on new aircraft or new panel installs. Um, yeah, so this is where things are going to get a lot more sporty. Now that you understand how radio works, or at least have kind of like a high level understanding of radio principles and components, now we're going to put that to work explaining like how VORs operate or how GPS operates. And so that way you can kind of get an idea of how a lot of these systems operate and how they talk to each other. We're going to pull up the 737 GenFam and we're going to show you how these systems are employed on a 737. Then we'll simultaneously be pulling from the 8083 to show you, and it's always going to be kind of like geared towards the general aviation crowd. They're changing that a little bit, but a lot of the graphics are still kind of dated and like definitely kind of GA focused, which is fine. It's a good way to build a solid understanding, and then we'll use the FAM graphics to help articulate that understanding towards our heavy commercial bias in the course.
Okay, so this is going to seem a lot like a really big history lesson to you guys over time, but really that's kind of the story of radio navigation and avionics is that it's slowly been progressing, and it seems like every time we manage to get one technology in place, a new one comes out that displaces that other technology. But we're going to start with non-directional radio beacons, or otherwise known as automatic direction finders, ADFs, and that's going to be on the far left-hand side. And you'll notice that it was developed and implemented in 1920. But you'll also notice that it's still in use. And so, yes, like every 737 and every like heavy commercial aircraft that comes out of a factory still has the ability to track ADFs, believe it or not. So that's over 100 years of radio navigation already, and that's pretty cool. Like when I just kind of stop and appreciate, think about look at all the rest that's on that chart, how cool ADFs actually are. So let's talk about what an ADF actually is and how it works. Okay, so whenever you hear the words homing beacon, that's what you want to think about with an ADF, because that's effectively how it works. So here I'm going to read you a kind of paragraph out of the 8083, and that will get us going. An automatic direction finder operates off of a ground signal transmitted from a NDB, which is a non-directional beacon. Early radio detection finders, or RDF, use the same principle. A vertically polarized antenna. Remember antenna polarization from the last video. So it's vertical, so the lobes make like a donut that's flying through the sky, like it's stood upright rather than sitting like down like it's on a plate. So it's a vertically polarized antenna was used to transmit radio waves in the 190 kilohertz to 535 kilohertz range. A receiver on the aircraft was tuned to the transmission frequency of the non-directional beacon. Using a loop antenna, the direction to or from the antenna could be determined by monitoring the strength of the signal received. This was possible because a radio wave striking a loop antenna broadside induces a null signal. When striking it in the plane of the loop, a much stronger signal is induced. The NDB signals were modulated in unique Morse code pulses, enabled the pilot to identify the beacon to which they were navigating. All right, so that is a long-winded way to say that basically they tuned into a radio station, and as they flew up to it, the Morse code, it has a 2-digit Morse code identifier. It'll be like beep 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 beep. Like it'll get louder and louder and louder and clearer and clearer and clearer. On the dash of the aircraft, kind of like in the center of this airplane that you're looking at, you'll have a compass card with an arrow that's pointed to it, and so the airplane will say like, "Hey, look, I'm flying this way," and then the direction the ADF is striking the plane is this way. Now, if you take that direction from the radio station and then you know what your heading is, then you can kind of just simply like chart two lines, and then where they come together, you're like, okay, well, we must be here, and that was a way to kind of find out where you are. The other way is just simply to fly to the radio station, and so you will eventually get to like where we're talking about Victor ways, where there were like essentially like little paths the airplanes could take to fly from point A to point B by using these types of radio navigation aids. Another thing that you could do is that there's an overlap, like we were saying in the last video, between ADF and AM radio stations, and so you could tune into AM radio stations, and as they got clearer and clearer, you knew you were getting closer and closer, and then the needle would also point towards where that radio station was coming from. So if you knew that Texarkana's AM radio station was 790, you could tune it to 790 and start listening for Texarkana, and the closer you got to it, all of a sudden you would pick it up, and the ADF needle would say like, hey, look, you need to turn a little bit left or a little bit right to fly towards where that radio station is, and that would get you like, in the ballpark. Now granted, this is like 1920. It's not perfect. Like there's going to be, it's not, you're not going to fly right up to the runway like you would today. And it took a lot of work to do the. I mean, there's a reason why there's like in old bombers there's like a navigator station. That's what this guy was doing. Is he was trying to figure out. And try to figure out and understand exactly where the plane was at and where it was going and all that good stuff, and then tell the pilot what corrections he needs to make. So he's worried about flying the plane like where it is right now, and the navigator's trying to figure out where it's going. So this is not the most perfect way to navigate, but it was way better than just simply like flying down the road and like looking out the side and hoping that you don't you run into any weather or anything else like that and just fall on the road. You'll talk to old guys who used to navigate this way, and they said that they would fly to like Malvern's one that's local for us. I don't know where you're listening from, but essentially, like you could fly directly to Malvern, and over the Malvern Airport, on the top of one of the hangars, it said Malvern really big, and so you knew you were at Malvern. And so if you were at Malvern, the next step you needed to do was tune into like Hot Springs, and you would make a left-hand turn, and you'd start looking for the next ADF at Hot Springs or the next AM radio station. And you would fly until you saw a big building that says like Hot Springs, and then the ADF would flip, the station would get super duper clear, and we would know, like that's where they were at. So that's the way that people used to navigate. But it's still being in use today. It's like on a 3.7, you can tune the ADF to it. Like I've told you guys in the last video, I was working on a 6.7 and would put Sherlock Holmes from the AM radio station downtown Seattle on and listen to it while I worked. And so these are still, even though it's 100 years old, it's super cool that it's still actually in use. Okay, so let's talk about these loop antennas. Now, these antennas are actually kind of iconic for those 1920s, 1930s, and into the 40s, and even up to the 50s aircraft, depending on where you look. They are highly, highly, highly sensitive to direction because of the way that they are lobed. And I'll put that donut graphic up. Now imagine like looking at this antenna. Imagine like you had like kind of like a donut of sensitivity that kind of like just are outlined around that loop. As signals hit it from the front, it says like, hey, look, this is the direction that's coming from, and then you could turn the plane towards it. Later ADS would actually have antennas that would just turn directly to it and then null the signal out. And once it was nulled, it would say, okay, this is where we're at, and you would get an indicator in the cockpit. Hey, like it's at 9 degrees from us, and it would just track that null signal all the way around. Now, modern ADF antennas use two internal antennas in a small hockey puck. We've just progressed. We don't need the big like loop antennas like you saw back in like the 1920s anymore. Nowadays we can do a lot of the same sort of detection electronically, but modern antennas have they look like a little teardrop like you're looking at the on the screen there, and they project a couple of, they use two different antennas that are wound coils that actually project the same amount of sensitivity that the older bigger loops did. We just simply got better at constructing them. Now what they do is that it'll have multiple loops projected out, and you can see on there the pattern loops and the pattern of sense. And as those patterns get disturbed by incoming radio signals, they can then correlate exactly where that signal originated from based on the strength and the place where it disrupted the patterns at, and then cross or you put that those two disturbances together, and you kind of get a spot on the map where it must have originated from. It's just like any kind of triangle. It knows the distance between the front antenna and the rear antenna, and once it has those 2 points, that's one leg of the triangle. Then all of a sudden, if we can make a guesstimate that, like, hey, look, this signal entered in the pattern of loop, field at this angle and at this strength. Well, the strength will give us the length of the last triangle, or the last leg of that triangle, or a leg of the triangle, and then the direction it hit it from will give us an angle to shoot from, and that should also correspond with the pattern of sense antenna. That you should see a slightly less strong signal, or since it's a little bit further away from the station, and it should have hit at a different angle, and that angle will then allow the ADF to project exactly where the station's at. And if it knows where the station's at, then it's just simple math to say, like, okay, well, where am I at? And you just reverse azimuth it, and that's what goes on to the card in the cockpit that lets the pilot know, hey, look, it's 9 degrees to our left, or whatever, bearing 1/8, so that is ADFs and how they work. Okay, so this is what the ADF system looks like on the Max. So as the Max flies around, you've got 3 key components for the ADF. You have the ADF receiver, which is that LRU. There should be 2 of them in the 4D and eBay, and it looks like that. It's made by Collins. Just simply slides in there into the rack. There's a plug on the back side of it that plugs up to it, and then you have little tie down fasteners what's that? That's what those 2 little screws are in the front and the bottom. It just slides over the top. You tighten them down, and you're good to go. You have the control panel. So up in the cockpit, you'll have an ADF control panel that you can dial it in. There's other ways to do it as well. You notice that the ADF receiver on the graphic there ties into DPC2. And then that'll actually pull up on your nav page if it's selected on the display, and you can tune the ADF that way as well. And it also has the combined loop and sense antenna, just like we were just talking about, and it looks like a teardrop on the top of the cockpit, or the top of the fuselage, and it needs to be oriented a very specific way. And it's something on all ADFs, not just the Maxes. They have to be oriented correctly to read correctly. If you put them in weird or off kilter or kind of haphazard, they will not read correctly. The last thing to kind of talk about is that you notice that it goes to the REU, the remote electronics unit, and then off to the speakers and headphones. That's basically saying that, hey, look, you can listen to these ADFs to get the Morse code, or you can listen to Sherlock Holmes if you want to tune into a AM radio station with them. And that's the routing that signal goes through. The ADF receiver picks it up via the antenna, and then it'll pipe into, it goes into DPC2 for sure, but you can't listen to it that way. It goes in, anyways, the audio signal goes into the REU and then out to the headphones. You just have to go to your audio control panel and just select ADF on there, and you'll be able to listen to it. All right, so as you kind of like look at the timeline, you get into this frenzy of innovation. So we start off with ADS in the 1920s, and the next thing that we go to is the low frequency radio range. But it only really lasts for up until the mid 80s or so. We won't go into those because you just simply won't see them anymore. Effectively, you just flew to the tone of some beeps based on where you were at. You would turn it on, listen, and then make a course adjustment. That's not really that practical for a bunch of different reasons, to include having to talk to ATC and everybody else and people inside the airplane, and then listen and try to figure out where you were navigating to. So it naturally kind of like went away. The next one that gets implemented is Lorenz. Lorenz basically was kind of like we'll talk about ILS here in a little bit, but it's kind of similar to that in that you either steered left or right to track the station. It only lasts until the 1960s, and it gets replaced pretty quickly. So it just wasn't as effective. Then you get into in the 1940s, we see the rotating multi-beam aural range. Now this becomes interesting because it effectively becomes the pre-runner for VORs. Now VORs won't. We'll get to that here in just a second. But they don't come online until 1946. But the Sandkassel, rotating multi-beam aural range was the first step towards that. But it had the same problem with LFR, is that like it was aural only. There was no dial indicator that actually allowed you to see it. And here's the problem with that, is that not only would you have to listen for it, and you'd have to fight all the noise that's going on in the cockpit, but and you couldn't see it, but you also can't integrate sound very well into other systems. Whereas if you have a visible display, that means that there's a signal that has been interpolated into something mechanical that's in front of you. And that means that you could also turn around and integrate that into your autopilot, which you can do with other systems. But we'll get to that here in a minute. So hyperbolic, so this becomes like kind of really big in like late 19 or the early 1940s is when it comes in, but they actually last for a pretty good while. Specifically, Loran. And you'll hear some of these older pilots that it really started making its way into GA in like the 1970s, and people were like, "Oh, Loran!" Like it was like the coolest way to navigate. Well, GPS really kind of like killed Loran. Loran was originally built for maritime use, but then got adapted to use for airplanes. So that one's gone. You won't see Loran anywhere, and you definitely won't see any of the other systems like Omega or Deca or anything else like that. All right, then the next one you have VARs. So that's the visual aural range, which is very similar to the LFR, except for now that there's actually a display. So they're like you could still listen to it, but now we have a display for you to fly to. It still had its challenges and kind of went away in the 1980s. Definitely getting replaced by things like Loran. If you're a GA pilot or a commercial carrier ordering a plane from Boeing or Lockheed or somebody like that, and you look at your options for navigation, and they put you like a Loran on the table and a VAR, well, it was pretty easy who you're going to pick. The Loran was clearly the superior option. However, there is one that is still in use for now, that a lot of people will still train on and still use. It still integrates well with your autopilots and all that other good stuff. And that is the VOR, the VHF omnidirectional radio, or well, it's VOR, yeah, VHF omnidirectional reference is what VOR stands for, but it's a visual multi-course range device, and that is what we are about to talk about. Okay, let's begin just trying to understand what a VOR is. So, VOR produces a signal that transmits and propagates 360 degrees from the unit and are used by the aircraft to navigate to and from the station with the help of an onboard VOR receiver and display instruments. A pilot is not required to fly a pattern to intersect the signal from a VOR station, since it propagates out to every direction. The radio waves are received as long as the aircraft is in range of the ground unit and regardless of the aircraft's direction of travel. So on the graphic that we're looking at now, that airplane could fly anywhere as long as it's tuned to the VOR that has the right frequency in the nav radio that's tied to that VOR. The VOR will simply just tell it, "Hey, look, you are from the station at 280 or 315 or whatever the direction happens to be," and that allows you to do a lot of things. If you have multiple VORs in there, you can tune to multiple VORs at one time, and then you can turn around and say like, "Okay, well, I am to this station at such and such a degree, and from this one at another degree, and then to this one at another bearing," and then you basically start. You take your sectional, lay it out. You'll draw a bunch of lines, and where they all intersect, that's where you're at. and that it becomes a pretty accurate way to navigate. And this is the way that people have been navigating for a long time. The only even with the other implementation of other types of radio navigation, VORs were kind of like they were the stalwart mode of navigation for years, even with Loran and all this other good stuff that came out. Generally speaking, most people preferred VORs, and so like during your instrument, your private pilot check ride, this is what you were going to get checked on. You were going to get you know graded on basically can you tune a VOR, can you navigate to where it is you want to go, and then they would ask you a bunch of questions about that kind of thing. So VORs have been around for a hot minute, and they probably will continue to be around for a while because it adds at least a layer of redundancy to the radio navigation spectrum. Even though GPS is actually way better and simpler and easier to use, VORs are kind of like a low cost way to make sure that everybody can still navigate, even if like you had some kind of mass GPS outage. There was like some sort of like cyber attack on the U.S. that took down all the GPS. The radio stations are they're pretty independent of all of that. So as long as the VOR is up and running and being maintained, it'll kick out the transmissions that you need to navigate to it. Now they also have an identifier that you can tune the nav radio into. So like you'll go to your nav radio, you'll tune to the frequency of the VOR. You'll see it on the indicator. It'll kick the needle the right way, flip the flag that says either to or from, and then you can put your headset into it or selected on your audio control panel, however the airplane works, and it'll put out a Morse code. Whereas ADF was 2 digits, these are 3 digits, and so you'll get a 3-digit Morse code beep that lets you know that, hey, look, I'm listening to this station, and that's important because some VORs you might get the get the frequencies confused or think that you're tracking one, but you're actually tracking the other one. And so it's always good to tune a VOR, then listen to it, hear the dots and dashes, write them down on your knee pad, and then check and make sure that you're on the right one. And so that's why that feature of a VOR exists. All right, so let's look at this VOR indicator. We're just we're gonna start in the top left, and we're just going to go clockwise and talk about all the little features of it. So first off, you have your course index. That's just a fancy way to say this is where you're headed to. So like you're flying that direction, and that card will either, depending on the type of indicator you have, the card will either spin around or the course index will spin around and let you know where what radial you're on for the VOR. Then you have the unreliable flag signal to the right. So that's basically means that like something is not correct, and so it's saying like, hey, look, this is what the VOR is saying, but there's reasons to indicate that there's a failure either in the signal, there's a failure in the unit or on the display, or something is not right. So you need to take everything that this display is telling you with a grain of salt. Then you have the to from indicator. So that will so when you think about to, you could be on a radial that will say like, hey, look, I'm on the 1-8 radial to the station. So that means that the station is north of me, and I'm flying up from the south to the station. But then as I fly over it, that flag will flip and say like, hey, look, now I'm going away from the station, and so I'm from it, heading away off into the north with the station behind me, and you'd be on a 3-6 radio at that point. Okay, so then continue going around the OBS knob. So that means that Omni bearing selector. It means that you can grab that thing and spin it around. That's just how you kind of operate the display. Then the next one up is approximately 2 degrees in VOR mode. So that means that like if you were off, so like keep in mind that the VOR, if you're gonna select to fly a 3-6 radial, like that's what this one is indicating. and you're tuned into the radio to the nav radio to the VOR. Select your radio with your OBS knob of 360 in this case, and then that CDI needle that we're getting ready to talk about will be kicked off, way off to the side. And so what you're going to have to do is fly until you intercept that radial from the VOR itself. So remember, the VOR is just a station; it's a fixed point in space, and it's going to kick out 360 degrees of radials all the way around. You're going to select which radial you want, and you're going to fly to that radial. So if you want to be on a 3.6 radial to the station, that means that you're going to have to fly, a certain way to intercept that radial, and then from there you're going to keep on tracking it to the station or from the station, depending on which you have selected. That CDI needle will tell you how far off you are from it. So if you're off to the left there towards the words, you're 2 degrees off every tick mark. So the first tick mark is like you're 2 degrees off that 3.6 radial. If the next one is 4 degrees, and so on and so forth. And so that tells you how aggressive you need to be on the controls to fly back to get back on course. And so then we've kind of talked about the CDI needle there. So now let's look at what a VOR, the antenna itself, or the ground station and the antenna for that matter, look like in the real world. Okay, if you're ever driving through a field or something, you see one of these things. That's what a VOR looks like. That's the antenna of the ground station that actually transmits the signal, and they're all over the United States. You've probably driven past a dozen of these things and never paid any attention to it because it just looked kind of weird and they're not really any kind of. There's no flash to them. There's nothing's going to call your attention to them unless you're a pilot or a mechanic and you know what they are. And then also it becomes kind of cool to see them. But they're all over the place. They can be up on top of mountains. They can be out in cow pastures. They can be inside cities. It just depends on where they were placed. Now, the VOR system, keep in mind, it's nearing 100 years old. It's been out for a hot minute, and whenever they were selected, those sites were selected. They were selected so that they'd have like free range to transmit all the way around unobstructed. Some places that they still struggle because they're in mountainous areas and stuff, but generally speaking, that's why you find them a lot in pastures. There's just nothing around them, and so that's where they placed them, or up on top of mountains and things like that. But now, as time has progressed on, I think it's almost 100 years, there's been all sorts of things that have been built up around it that interferes with the VOR signals. And so there's a whole effort to try to figure out how to fix that. But that's what a VOR looks like. Okay, so here's on the left another example, just another VOR. But here's the symbology that's on a sectional map. So if you figure like a sectional map, which is an airways map that pilots will use to navigate, this is what they look like. You'll always have in the center the VOR symbol, which there are 3 different variations of, and then the radials that come out around it always in blue. So that way you understand, hey, look, this is a VOR. Anyway, so the 3 different kind of symbologies on the right hand side there, you have that is just a VOR. There's no extra capacity to it. Above it is VORTAC. So TACAN is a military radio navigation system that was integrated into a lot of VOR stations. So you'll have VORTACs. Then you also have TACAN stations that are just off by themselves as well. And then at the bottom you have a VOR DME. The DME stands for Distance Measuring Equipment, and we're going to talk about that one here in just a minute. Okay, so on the airplane, what do VOR antennas look like? They can look like any one of these. I will tell you the most common one are going to be the second from the right, the little V wires, and typically they're going to be affixed to the vertical stabilizer right there, and they'll come out with the V's kicking out aft, so kind of like an arrow point going into the wind. But there can be other ones, so like blade antennas are also used. That's what's on the Lear. You'll see that a lot on jets, where they don't want to have image is very important. The way they look, they're not really optimized for pragmatism. They're more optimized for aesthetics, and so like the blades have a very subtle, subdued view, or kind of like aesthetic to them. and so that those will be used. You generally won't see the those loop antennas. They're definitely out there, and there are some aircraft that will have them. Matter of fact, on top of my head, I think Chinooks actually have those in the Army. But and they're just another type of VOR antenna. They work just fine. They're just them being a loop kind of creates or it can create some some problems, some hazards and stuff like that. So they generally kind of stay away from them. But they you could be called on to remove and replace one or troubleshoot one. And so just know that VOR's antennas can look that way. Okay, so another antenna to look at. We're going to start with the antenna that's located at the very tip top of the vertical stabilizer for the 737 Max. But it's just a little blade. It'll be stuck off to the side, and you'll be able to see it. And there should be two of them, if I remember correctly. Those pick up the VOR signal and they send it to the IMMR, the multi-mode receiver. There's all kinds of things that multi-mode receiver can actually do. This is just one of them, but it will basically send the VOR signal into it, and it processes. Now you control the VOR. You can control it with the nav control panel right there that's on the top left hand side of the graphic. You can also control it on the display itself if you so choose. But anyways, once it gets the VOR signal, it kicks it out to three places. One, we'll start with the bottom, the REU, which allows you to listen to the Morse code just like the ADF did, same concept. The other one, there's a whole host of things the VOR goes out to. The FMC is the flight management computer that allows you to say, hey, like this is where we're going and where we want to go, and calculate fuel and runway length and blah blah blah, all that good stuff. The FCC, I cannot remember what the FCC is off the top of my head. I'll come back to you on that one. But anyways, the HUD is the heads-up display unit, so it'll put all your navigation data right there on the HUD in front of your face, so that way you can fly it. And then the DFDAL is the digital flight display acquisition unit, which is basically kind of like your black box recorder. It's basically recording all the things that happen on board on the plane. Then the DPC takes that information and transposes it into fiber optic. Then that fiber optic line goes up to your. Actually, I take that back. The fiber optic line is just an input into the DPC rather than an output. So the output is a regular wire line that goes up to the displays, and so you can. Up there on top, there's a switch. There's like both on one, both on two. You can flip it to be on the co-pilot or the pilot side, depending on what you want. And then that navigation display, we're going to look at here again just a second. But that kind of takes it's the same information that was on the VOR instrument. Display that we looked at earlier. It's just been digitized, and so let's look at that a little bit more deeply. And the FCC is the flight control computer, as a brain fart on my part. It's that basically will tell you like, hey, look, this is the position the flight controls are at based on these inputs and these conditions. We need to do certain things, like and we'll get into that a lot more whenever we get to flight controls. So sorry, just blanked on that one. Okay, so this is what the VOR looks like. On the Max, you have these two options. You can do the full screen or you can do the half screens based on how you have it set up. We're just going to kind of take a quick look at it. All over the compass radials, you'll have the heading bug. That's where you want to go. That's where you're tracking to go. You have the CDI needle that's been displaced by 2 degrees off to the left, and then you have the radial that you actually have selected with that magenta line going to 1.8 there. And you can tell that by VOR1 on the top right-hand corner. That's on the Seattle VOR, and it's on 180 has been selected. On the opposite side of that display, looking at the full display, is the wind direction as well, and that's where you get that 325 at 15. It means that's 15 knots blowing at 300. So they got a little bit of a tailwind that's hitting them. from the other side. So you think a reciprocal heading of what is 1-3, so you add 180 degrees, that's about 325. If I did my math correctly, it's or in that neighborhood. But the other thing to take away, on the bottom left hand and the bottom right hand screen, you have two different VORs. You have VOR1 Seattle, that's one that's selected and it's actually being used, and then you also have VOR2, that's PAES Painfield, and they're going to give you a distance for either one of them. That's we're gonna get to the DME and how that works. But if you notice that VOR1 in the top right hand corner, DME is reading 18. You see that 18 at the bottom left hand corner by VOR1, and then off to the right it's 23 miles. I don't think those miles are correct because Painfield and VOR and Seattle are a little bit further than 7 miles apart. But who knows where this airplane is at? Maybe they're splitting the difference between the two of them. The same information's on the right hand side of the half screen. It's just it's been condensed down so that way you could have another display up. So like you have, as a pilot on a 737 Max, you have two full displays, and so you could have like your flight instruments on one, and then have all the navigation on the second one, or split it up into where you could technically have like four different things displayed at one time, depending on what you're doing, what you're trying to manage. But that's what a VOR display looks like on a 737 Max. Okay, so often integrated into a VOR is distance measuring equipment, or DME, and you'll see that just like we saw on the symbology on the sectional. It'll have like a little square on the outside of the VOR to let you know that it has distance measuring equipment. But how does it work? So the DME it basically transmit, or the aircraft transmits a carrier signal that is modulated with a string of integration pulses, so it's pulsing. Boom, boom, boom. The ground unit receives the pulses and returns the signal to the aircraft. The time that transpires for the signal to be sent and returned is calculated and converted into nautical miles for display. Time to station and speed are also calculated and displayed. So basically, it's sending these pulses out. The DME station grabs them, sends them back, and that gap in time between the transmission and the reception will allow the airplane to say like, oh well, if it took 10 milliseconds, it must be 10 miles, or however that math works out to be. And that the reason why that's super important is that now we have a distance and a direction from a radio navigation. So if you have a DME that's integrated with the VOR, that means that you could be flying and you know that you are exactly 090 from this station for sure. Like that's what the VOR is telling you. But if with just the VOR, you don't know how far you are. You could be anywhere on that. It could be 10 feet to your left, and that's going to read the same thing, or it could be 10 miles to the left. You don't really know. But with the DME, it gives you that distance. Now, that means that one VOR DME station can tell you pretty much exactly where you're at. The DME is like really, really accurate, and the VOR also is accurate down to just a few degrees. So if you have those two data points with the high level of fidelity, then you can pretty well know exactly where you are at on a sectional. You can say, hey, look, I am at this bearing at this range, therefore I have to be there. You throw another VOR DME station in, you're going to know exactly where you're at, because it's unlikely that both of them are wrong in both of the same ways, and so you should be able to plot that on the map, and then look out the window and see the mountain that you're trying to avoid, or whatever, and just use general pilotage as a check. Okay, so let's look at what does a DME look like on a 737 Max. All right, so the DME ground station is where the signal will start at, or will be received by the aircraft that's transmitting it. That's something we didn't cover in the last graphic, is talking about the slant distance. So all the slant distance is the distance from the actual airplane to the ground distance itself, but that's going to be referred to as slant range distance, or slant distance, or slant range. But anyways, the first hardware we need to look at is that small blade antenna that's right there. It's going to be located on the bottom of the airplane. There's usually two of them because there's usually two different DME systems. And on these heavy commercial airplanes, there's almost always two of everything. But yeah, so just for redundancy. So there, it starts with the antenna, then it goes to the DME integrator. It's a humongous box for what it actually delivers. It's made up by Collins. It's placed on the E-rack, depending on the configuration. I thought about actually putting up the E-rack and kind of like going through all the different boxes and where they're at. But the reality of it is like different carriers, different configurations, different models of different airplanes will have a bunch of different. So we want to do don't want to waste any time. So the DME integrator is the heart and soul of the DME system. The navigation control panel controls it. The FMCs, or the flight management computer, can also integrate with the navigation control panel, and it can be commanded by it. But really, there's going to be a conversation between the DME integrator and the FMC based on like how far things are from point A to point B, because that's going to in turn dictate how much gas can be calculated, like what speed, time to distance, all that good stuff. Like is going to come down to your to FMC, and then it'll also kick out a signal to all your different digital flight control unit, your DPC2, your HUD, all of that stuff, and then also the DME, because it has a two-tone Morse code tone. It's going to go to the REU and then out to the speakers and to the headphones, headsets, and stuff like that. Ultimately, it will be displayed on the navigation display. We won't look at that again because it's the same. It's integrated into the VOR display, so we talked about it a little bit. That it'll give you the distance to the station, so you'll tune into VOR DME. It'll the flight display will say, okay, well, this is what the bearing that we're at from it, and it'll also say on there like, hey, look, you have so many miles until X, Y, or Z. The primary flight display system, that's just, it's set up so that way you have your flight control, or your flight display on the top right hand corner of that primary flight display block, and with the DME information that's also put into it on the bottom, on the bottom right, I guess third it is. But yeah, so that's what the DME looks like. It's like, it looks way busier, and I guess it is way busier than it probably needs to be, especially since it's an older avionics system. That all it does is tell you how far away you are from something. That seems like a small thing, but it's actually a pretty big thing. But yeah, all right. So now let's talk about GPS and how all this has been replaced by something more accurate. Okay, so GPS actually starts right here with Sputnik. It was a little small gray satellite launched into orbit that caused everybody to absolutely freak out, because what that basically insinuated is that, like, if the Soviet Union can put a small satellite into orbit, then in theory there's nothing stopping them from putting nuclear bombs into orbit. And so you gotta look at Sputnik in the context of history. A lot of people were just justifiably, just completely freaked out by the fact that the Soviet Union had this capability. Everybody except these two cool cats. That's William Greer and George Whiffenbach on either side of their boss there. They sat back during Sputnik, and they noticed that since it was transmitting a little beep. Now, that's all Sputnik really did, is it went around the Earth and went beep, 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 beep. And so once they realized that you could do that, they could use the Doppler effect to effectively pinpoint exactly where it was. And that's how they were able to say, hey, look, it's circling us 15 times a day, because we could hear it come around and we could know exactly where it was going. And so they sat back and said, like, what if, since we know how the line works, if we know where one end of the line is, directly back it gives us the other end of the line. It's like, what if we had a bunch of these satellites, and then we started to listen to all of them? Then mathematically, we'd be able to pinpoint where we were in relation to those satellites. And then they started to kind of churn through that idea. The next thing you know, they're pitching it to the Air Force and the Navy. And by the 1960s, the first kind of proto GPS constellation was in orbit, and they were playing around with it. This keeps on going and keeps on iterating to where they're like, okay, well, that didn't work very well. Let's see if we can tweak it again, and we'll do another thing. To all the way you get to the Omega systems about in the 70s, whenever Loran is really really big, and that becomes kind of like the forerunner to GPS, but it wasn't quite there yet. So they keep on doing these multiple iterations. The military pours a lot of money into it, and then by the 1990s, the Gulf War comes out, and it was revealed to the world that we could take a Tomahawk cruise missile and literally put it through a window on the other side of the planet. And people were like, "How in the world does this work?" Well, it was because we had high fidelity GPS at that time. We had enough satellites up in orbit that we could with a high degree of certainty calculate down to like the last square inch of a point on the Earth, and then just simply integrating it into a guidance system of a missile wasn't really that difficult to do. And so that's whenever you see people like Garmin coming online and start offering it across the world to these different applications. All right, in 1989, these two guys, Gary Burrell and Min Kao, in Lenexa, Kansas, started what would become Garmin, which would go on to completely change the way that we live our lives. I mean, I have a Garmin watch on right now, and there's Garmin avionics in the airplane, and all that good stuff. They originally came out once the technology for GPS was known to the public and it could be used. They created a company called ProNav. Now, ProNav basically created a unit that sold for about $2,500, which is a lot of money today, much less 30 years ago now. And so they started selling these ProNav units, and then before long they realized they needed to create a company that had a much wider aperture, and that they saw that their device could actually be used in automotive, aviation, marine, outdoor, sport activities. I mean, it was such a broad-based approach to navigation that if they just simply used it correctly, then it could be, or if they developed it correctly, it could be used across all these different spectrums. So they created a new company and they took their names and they put Gary and Min and pushed them together and made Garmin. And so today, Garmin is probably the foremost navigation system or brand that you'll find in aviation anywhere. The G1000 was the first ever panel that came into the cockpit that really seemed to just completely revolutionize the way that we did even engine monitoring, the autopilot integration. I mean, you name it, that G1000 would do it, and it was the first time it was available to the common man. And that stuff had been there for a while in the heavy commercial stuff, but it really kind of changed GA specifically pretty substantially. Yeah, so that's the history of how we got to GPS now. Okay, so now that we know the history, let's talk about trying to understand how it works. So most like radio navigation systems, they operate with a ground station that transmits a frequency and the airplane tunes into it or somehow interacts with it. GPS, just strict GPS, because we'll get into WAS here in a minute. It does not use a ground station, which gives it some very distinct advantages. Like you have, since you always have satellites overhead, you don't have to worry about line of sight. You will always have a multitude of GPS satellites, especially now because there's such a huge constellation of GPS satellites up there now. That means that the more satellites you have, the greater fidelity you have on the data that's going to determine your position. The more redundancy you have. If one station goes down, you don't lose an entire area like you do with a VOR. If you there's like one Texarkana VOR and you're only navigating to Texarkana with via VOR and it goes down, well, you're going to have to kind of interpolate or guesstimate on how to get here. You don't have that problem with GPS because there's so many satellites that are up there, and so what all they're effectively doing is triangulating where the airplane is relative to those three satellites, just like those two guys did with Sputnik. Like, we know the time it takes for a GPS signal to leave the satellite and come to the airplane, and we know how to receive those satellites and then time them. And so, like on those signals, it will have a unique satellite identifier and a synchronized time whenever the signal left, and that's what it transmits. Well, then when the receiver gets that, it says like, okay, well, it came from this satellite, which we know to be at this orbit at this time, and like it took me so long to get here, so therefore I have to be like within a certain amount of distance from that satellite, and then a certain bearing from that satellite. But whenever you get that across the board of like 24 different satellites, and you're getting all this information in, well, that becomes, you slowly start to take the Venn diagram of like where you could be, and you start to shrink it down pretty substantially.
Okay, let's talk about another feature with the GPS. So pay attention to the black right now. That here's our airplane, we're flying along, and it's receiving a GPS signal, and that's pretty accurate. It knows, basically, like, because I know where the satellite is, and I'm flying along, and I get a signal that says like, hey, look, I'm at your XYZ bearing at such and such a speed at such and such a distance, and therefore I the airplane can interpolate that I must be about here on the map. But there's variances. There's things that could happen that could throw that off. Interferences, calibrations, you name it. Electromagnetic interference from the sun. And so that gives me this black arc that I think I'm right here, but I could be 10 meters off in any one direction. So that gives me what's called a figure of merit of about 10 meters, or FOM 10 meters. All right. So how do we get to where we know exactly where we are? No questions asked. We start getting other satellites. So we get the blue satellite, the purple satellite. We get as many satellites as we possibly can. And all of a sudden, these figure of merit start overlaying each other. And then all of a sudden, we start to eliminate the areas that we know that we're not by simply seeing like where all the circles intersect at. And that helps take our 10-meter figure of merit and shrink it down to like 1 meter. Now, believe it or not, the mathematical roots of this actually go back to World War I with artillery rounds, and if you can delve more into it. It's called a Kalman filter, but that's basically how GPS knows where you are, and they know it so accurately. Now, as time would progress on, there's other ways to make this even more accurate, because as the airplane goes over the Earth's surface, we know exactly where, like, we'll say there's a house right there on a church on the Earth's surface, and we know its position 100%. Well, as these satellites start talking to that house, and the one satellite says like, you are at such a coordinates. Well, that house knows where it's at. It's a fixed position. And so that means that we know that satellite is off by just a hair, just like this, whatever it's just a little bit. And then the next satellite comes up and goes, well, you're off, but you're off this way. You're off to the left. He was off to the right. And the other guy comes in and says like, hey, look, you're spot on, whatever. All of a sudden now we have like a mathematical correction that we can do to those signals as they start to come in. And then from there, we can push that information back out to the airplane and says like, hey, look, because I know these satellites, here's the corrective data, and I'm going to also transmit a signal directly to you that says this is where I'm at relative to you. And so now once you have one of these, and then you have another one over here, and another one over here, and another one over here, all transmitting this data to the airplane, all of a sudden that airplane knows exactly where it is, not just on a spot on a map, on like a two-dimensional surface, but also three-dimensionally. Because keep in mind, it also knows where it's at relative in altitude to these satellites and to those stations. And that is what has become known as the Wide Area Augmentation System, or WAAS. So you'll start talking about GPS WAAS, and then you'll talk about here GPS approaches and GPS WAAS approaches and all the other good stuff. All it comes down to increasing the number of data points that the airplane can draw from to know where it's at, and correcting this figure of merit problem so that way the airplane knows exactly where it's at. This is the pretense, or the foundation for things like auto land. Like, it knows as it comes in. It's drawing from a bunch of different systems, but one of the primary ones is that it knows within about 1 to 3 feet of about where it's at above the earth, would not pay attention to anything else, just from GPS WAS to come in and land. This is how you park a Tomahawk missile in Saddam Hussein's bathroom window, is these types of systems, because they're highly accurate, they're highly reliable, and they're also highly dispersed. There's several different data points that are coming in. So if you have a problem with one, it becomes an outlier, and it's not useful, and you're starting to pay attention to the rest. This is where aviation navigation is going, and probably will go for the foreseeable future, until we come up with some sort of maybe quantum measure to measure where we're at. But this is GPS WAS, and you should know it in and out, because it's important today, and it's going to be even more important tomorrow.